All right. Good evening, everybody, and welcome back to Creation Myths. We have a live show tonight, and we're doing something a little bit different. So I'm really excited to be doing this one. Just making sure that everything here on my end, which it does. Does everyone just let me know, if the sound is okay, if you can see the slides that I've set up on the other screen here. Uh, but it sure looks like on my end we're good to go. So I think we're ready to talk about this, and this is a really fun topic. Now, before we get into the nuts and bolts of tonight's show, let me just explain what we're doing here because it's very different from what we normally do here. We are not going to talk about creationism at all tonight. That is just the opposite of what we're doing. It's not even relevant to what we're talking about tonight. Is just all about evolutionary biology. So what we're going to do here tonight and for the next 2 weeks after this, so next Wednesday and the Wednesday after that, is I'm adapting just little pieces of like the actual classes I teach and stuff that I think is really interesting and illustrates some really interesting evolutionary dynamics. And we're just going to do those. And what I want to do here is do this as close to kind of a regular class as possible. So, for those of you that are here live in the chat, please ask me questions. Just like in class, if someone raises their hand, they have a question that's relevant to the topic, I'll pause for a minute and answer that question. So I know that it'll be a little bit weird because I'm using StreamYard, broadcasting to YouTube. There's a little bit of a delay here between when I say something and when you all watching will see it live. But put your questions in the chat, and when I see them, if it's a relevant question to the topic, if it's something that we can, use to illustrate more detail and get a better understanding of what we're talking about, I'll pause, I'll answer that question, and we'll go from there. So don't hesitate to do that. Please, ask your questions, and if I can respond to them, I absolutely happily will do that. So today we are talking about how evolution explains virulence, and there's a couple of kind of things to understand as we go through this. So I always set my slides up for class like an outline. I've pared it down a bit because this is just actually part of a class I teach that's about 80 minutes long. We're only doing just one section of it. So the outline is a little more bare bones than it would be for like a real class, but it preserves more or less that same structure. Another thing to just kind of keep in mind as we go through this is you're going to see words that are highlighted bold and red. Those are like the vocabulary words. Those are your key terms. I really want you to be able to define those terms, right? If you all were my students, those key terms are a really good place to start in terms of like just making sure you have an understanding of this material. Okay, so I just want to make that clear before we get into it, so that you're not confused when you see kind of seemingly random highlighting on slides. It's very purposeful. It's not random at all. Now, before we get into the actual material here, I start every one of my classes with the learning outcomes for the day. And I do this in a very specific and kind of unique way compared to the way a lot of other people do it. So all of my learning outcomes for all the classes I teach are verbs. So basically, I want you to be able to do something with the content, with the material. It's not just know this, be able to explain that. It's go beyond that in some way, be able to kind of explain the material and make the connections at a higher level. Because I want you to demonstrate like an understanding to me, right? If you're my student, I want you to demonstrate an understanding of the material. So that means I structure things a little bit differently. So the outcomes for this topic that we're talking about right now are going to be identify virulence, just be able to like tell me what virulence is, right? And then compare and contrast the causes for virulence and the different hypotheses, and are they right? Are they wrong? Do they have support? Do they not have support? And then for the final section we'll get into today, compare and contrast intra and inter-host competition. This is a very important dynamic that we're going to see as we attempt to explain the evolution of virulence as a trait. Now, when I give exams for my classes, all of the questions are based on these outcomes. So like if I'm giving you a multiple choice test, right, I might say compare and contrast intrinsic and extrinsic disease factors. Which of the following is an intrinsic disease factor? And I'll give you, ABC or list, and you'll have to pick which ones, right? If I am doing an open-ended exam like I do for my smaller classes, not my giant class, my smaller summer classes get open-ended exams. An exam question might be compare and contrast intra and inter-host competition. Explain how each affects selection for virulence. And you'll have to write me, a few sentences to answer that question. But the point is that I'm saying up front what I want you to get out of the material. Here are the things I want you to get out of it, which are the exact things I'm going to evaluate you on later, right, on the exam. So that's how I always structure these. So because I'm making this basically as close to a class as I can, I'm structuring it the same way. And I want you all to keep in mind these outcomes as we go through. And my hope is that, we do this together. Or, hi, if you're watching this from the future, you watch this. And then by the end of it, you have a better understanding of these specific things. These are the big ideas I want you to get out of it. So everybody good? Everybody ready? So now we'll get into our actual material for tonight. So the first thing, our first section here is just the causes of disease. The first question we need to answer is, why do we get sick? And that is a surprisingly complicated question to answer. We could spend a solid hour just on this question alone, going through the different types of disease factors and what they all mean and how they all work. We're not going to do that. We're going to answer this very briefly, but this is a really kind of broad but good place to start for this topic. So we can break the answers to this question down into two categories. You can have intrinsic disease factors. These are factors that are inherent to the individual experiencing the disease symptoms, right? So this is going to be things like mutations, right? Genetic disorders, your responses to infections, things like a fever or inflammation. Could be physiology, right? So think about like diabetes, right? Type 2 diabetes. It could even be your morphology. So an example of that would be like how ankles are unstable and prone to being sprained, right? That is a problem based on your morphology, right? These are all intrinsic factors because they are inherent to the individual experiencing the disease. And the picture here, of course, is showing a red blood cell that is affected by sickle cell disease, which is, of course, a recessive genetic disorder. Genetic disorders are like the classic intrinsic disease factors. Okay, the other side, some of you can probably guess what the opposite side of that is. It's going to be extrinsic disease factors. So these are disease factors that come from outside of the individual experiencing those symptoms. So this is going to be things like toxins, which could be, via another organism, or they could be environmental toxins. Could even be something like radiation, right? Solar radiation. It could be your environment, could be an extrinsic disease factor. So like right now we've had a significant heat wave where I live, and that's an intrinsic disease factor. Long-term exposure to elevated temperatures can lead to things like chronic kidney disease, for example. But the one we want to focus on, the one I want to highlight, is pathogens. Pathogens, that word just means a disease-causing organism. So that's going to be like viruses, bacteria, could be protozoan parasites, things like malaria, or malaria's the disease. It's Plasmodium is the organism that causes the disease. And pathogens can even be like fungal, right? You can have fungal parasites. You can even have animal parasites like tapeworms or heartworms or flukes, right? These are animals that are parasites that cause disease. Anyone know what I have pictured here? Anybody know this particularly famous pathogenic organism? We're actually going to talk about this one quite a bit. It's really useful to illustrate some of the concepts we're going to talk about. This is a very famous one historically, just in general. Anybody know? I know there's a delay, so it's a little bit weird doing the ask a question, but anyone know what that one is? It's a very famous micrograph, that particular image of it. It's not E. coli. E. coli is bacterium. It makes kind of these filaments of the little pill-shaped bacteria. But yeah, that is Ebola. That is Ebola virus. It's this kind of weird filamentous twisted virus that's an RNA virus. Yep. Those of you who got Ebola, good job. All right, so now we've talked about intrinsic versus extrinsic disease factors, and we're going to focus on pathogens, disease-causing organisms. So let's continue on and talk about this topic, virulence, right? Virulence is a tricky thing to define because it takes so many forms. But kind of a good general definition for virulence is parasite-mediated morbidity and mortality. Morbidity means you get sick, and mortality means you die. Okay, so parasite-mediated morbidity and mortality. And there's lots of different ways virulence can manifest, right? It can be very direct, like Ebola that we just saw is very direct in the damage that it causes. It can be indirect, so think like a tapeworm. The damage that a tapeworm does to your intestines, it'll burrow its little head thing in there with the hooks and the suckers, and it'll make like a little wound in your intestines. But that's not really going to hurt you. The damage that a tapeworm actually does is the fact that it steals nutrients from you, and it can lead to a caloric deficiency or even like a nutrient deficiency. That's the actual problem. And then coincidental damage is kind of an interesting one. This is where like a pathogen, I'm going to kind of personify them a little bit when they accidentally hurt you. And the example I like to use for this one is poliovirus, because poliovirus infects your intestines. It's a GI tract virus. And in order to actually make you sick, like to get polio, like that causes paralysis, it has to mutate and get into your nervous system. But polio doesn't want to do that because that's a dead end. It can't transmit once it gets stuck in your nervous system. So that's like completely to the side of the actual replication cycle of that virus. But it's still virulence. It still can make you sick, right? And we could document virulence in all sorts of ways, right? You could see weight loss, you could see reduced fecundity, that refers to reproductive output. Of course, a higher death rate, right, is a really clear way to document, virulence, right? This virus has a higher death rate than that one. This virus is more virulent. So that's a very typical way to do it. Now, virulence is not an inherent characteristic of a particular pathogen or a particular organism. This is a really important thing to keep in mind. Virulence is due to the interaction between the host and the parasite and the context in which that interaction takes place. It's even going to change based on the genotypes of the host and the parasite. So somebody might have certain genes or certain alleles, which is a variant of a gene, that make them more or less susceptible to certain pathogens. So virulence, it's not just the pathogen, it's not just the pathogen and the host, it's actually down to these specific genotypes of each of them and how those factors interact with each other. Okay, so that is the concept of virulence. And what we want to do here is explain how and why virulence is going to evolve. That's the big question we want to answer here. Okay, so let's work on that. Here's the question, part 2 or part B, selection for virulence. And the question is, why be virulent? What's the benefit in terms of evolution, in terms of fitness? What's the benefit to being virulent? And kind of a question inherent to that is there a benefit to being virulent? Or is it just, oops, I didn't mean to do that. Turns out there's no upside to it, but it happened anyway, right? Is there a benefit? So these are the questions we want to answer as we go through this topic tonight, okay? So there's a bunch of different answers, right? It could be a side effect. It could be completely incidental to the infection, like the example I talked about a minute ago with poliovirus. Virulence could be due to within host evolution. You have competition between pathogens within a single individual, and that competition imposes selective pressures on those pathogens that make them interact with the host in such a way that it harms the host, right? That is something that could happen. You could also have virulence is actually adaptive in some way. It could facilitate transmission via disease symptoms. So like, for example, Cholera is a really good example. This cholera is a bacterium, lives in the intestine, or I should say it infects the intestines, and it creates a toxin that causes diarrhea, and that facilitates the transmission of the cholera because the bacterial cells then get back out into the water supply, which is how they get exposed to another host. So the virulence in that case actually facilitates the transmission of the pathogen. So this is an interesting one. I'll put this question up here. Fever is an incidental symptom that is the body fighting the pathogen. That's almost in like its own category, right? Because that's not even something that like the pathogen is doing. In all three of the examples that I have on screen here, right? If it's like a side effect, we'll call it, right? That's still the polio virus getting into the nervous system. Within host competition, that's the pathogen infecting your cells faster and more efficiently. And then, of course, disease symptoms are a thing that the pathogen itself is doing. A fever is almost a separate category where the pathogen doesn't do anything to you, but you still respond. And the response is what creates all of the disease symptoms. A classic example of this dynamic is going to be a common cold, right? You think about a cold virus, and there's dozens of cold viruses. They infect your upper respiratory system, right? Your nasal membranes, and it doesn't actually like hurt you that much. Like it's not going to destroy so many cells that it's going to like cause a problem. But your body still responds to it. You inflame those nasal membranes, you create a whole lot of mucus. So you're sneezing, your nose is itchy, your eyes are itchy, right? You have a runny nose, you're congested, maybe you have a cough. That's all you responding to the cold virus. That's a completely different mode of virulence that we're actually not talking about here, but that's a great question from Little Pink Bowser. And then there's a related question here from Max P. Where would viruses due to adaptations from other hosts in zoonotic viruses? We're going to talk about that in just a few minutes. We are going to get there, I promise, because this is related to one of the major hypotheses for the evolution of virulence and what those dynamics look like. So don't worry, Max, that's a great question. We're going to get there in just a couple minutes. Okay, let's keep going here. Now, here's kind of the conventional wisdom. The conventional wisdom is this. You have a trade-off, essentially, between virulence and transmissibility, okay? So to understand this conventional wisdom, I want you to think about the flu versus the common cold. Now, if you have the flu, if anyone's had the flu recently, you know what the flu feels like. When, like we've all had people be like, oh, there's a flu going on. Oh, yeah, I had that last week. I had the flu. No. If you were like, yeah, I had the flu for a couple days last week, that was not the flu. That was the cold. That was a cold. When you have the flu, your whole body hurts. You have a fever. You're in bed. You don't want to move. Like the flu is miserable. When you're infected with the flu, how many other people are you like seeing that you might potentially transmit those flu viruses to? Almost nobody, right? It's basically just the people in your immediate household. It's really bad. You are not moving. So it's more virulent, and that leads to fewer chances for transmission. On the flip side of that, consider the common cold, right? You have a cold. Now, a cold is like not pleasant, but it doesn't knock you on your butt like the flu, right? If you have a cold, okay, you got the sniffles, you got a runny nose, maybe you're sneezing a bit, but you're still out and about in the world. You're talking to people, you're interacting with people, you're touching doorknobs. So there's way more chances for that virus to transmit, specifically because it is less virulent. There are disease symptoms associated with it, but it doesn't actually prevent you really from like going about your everyday life. Now, as a public health measure, it kind of should, right? We should just be in general of kind of the idea that like, if you have a cold and you're sneezing, like don't be around people. But that's not how the world works. You're expected, at least in the United States, you're expected to like tough it out instead of calling in sick just because you have the sniffles. But that's a drag in a public health way, right? Because that just means way more people get colds than would otherwise be necessary. So this is the conventional wisdom, that there's a trade-off between virulence and transmissibility, right? How sick you make somebody and your ability to transmit to your next host. Now, I want to be very clear. there is some support for this. We do seem to see this dynamic in some contexts. Respiratory diseases, for example, not always, but many of them, you can kind of, if you were to like plot them, you would see some dynamic approximating this. But there are enough exceptions that you can't really put any significant weight on this conventional wisdom. There's enough variation in the dynamics, and there are enough other specific cases and other selective pressures pushing and pulling that we can't really apply this as a general rule, even though we might like to. It's nice and neat, and it seems to make sense, right? But we just don't have the ability, we don't have the data, this doesn't have the backing to be able to apply this as a general rule. So let's move on and find out what actually explains virulence when we see it, okay? Now we can zoom in and look at these dynamics for a virus. And what we're going to look at here in this plot on the y-axis is the number of viruses. And on the x-axis, we're just looking at the time of infection. And the red line is the number of viruses that you have. And you'll notice that we start here with, we're just going to say one virus gets into the cell, and then it goes to 0 before it goes up again. Because what happens when a virus enters a cell, right? It gets into the cell, and then it disassembles so that it can, replicate its genome and express its genes. So you went from having one virus that could infect a cell to 0 viruses. So that's called the eclipse phase. And if you kill your host during that phase, that's a really bad strategy because you haven't made any offspring yet, right? You went from one virus to no viruses, and that's not good. So how are you going to spread if you kill your host before you finish making more of you? So that's a bad strategy, right? Being too virulent definitely does inhibit your fitness. And in fact, even if you only make a few viruses before you kill your host, that's only slightly less bad, right? There are many viruses that actually have kind of biochemical ways of counting. One of the best talks I ever saw was a talk about a specific virus that infects a type of algae. And although I don't know if the host would be considered an algae. Anyway, it's a marine virus and it's marine unicellular eukaryotic organism. And the talk was how a virus counts to 1,000. And it was about how a virus regulates this dynamic. How does it basically replicate for a long enough time before it kills its host cell? And it basically has a way of killing its host cell based on a material that each virus has a little bit of. And when you have 1,000 viruses that have been built, that basically crosses the threshold and it kills the host cell and they burst out and they go and infect other cells. So that's kind of part of this dynamic. So we can see this conventional wisdom, this trade-off between virulence and transmission, also holding at a very small scale. Again, this is for, Max, this is for a single cell infected by a single virus, right? So it's one virus gets into the cell and then it goes away and then we start making new viruses. And the trick is to optimize the productive lifespan of that virus before it kills the host cell, right? That's the trick right there. So now we're seeing the conventional wisdom that has like logic behind it, but doesn't actually hold up. So now in part C, we're going to examine some of the major hypotheses for virulence, like what actually does explain virulence. And there are a lot of different hypotheses. We're not going to talk about all of them. We're just going to hit some of the big ones. And some of these hypotheses are better than others. There's no one perfect answer to this question. There are a lot of specific cases that are going to have very unique dynamics. And I'll explain some of these very specific cases that have their own kind of caveats to them. So we're gonna see a bunch of these. The goal, what we want to get to, is something approaching a general or generalizable answer. And again, there's going to be some specific cases that are just kind of doing their own weird thing. But we are eventually, after we get through this section and then the next section, we are going to arrive at something that does a good job explaining this in a kind of broad, general sense. Everyone doing okay? Chat, everybody doing okay? Everybody with me? Everybody following along? Not going too fast? All right, let us continue. So one hypothesis that we see all the time is there going to be evolution towards mutualism, which is where the two individuals, instead of being antagonistic to each other, right, a host-parasite relationship, they end up benefiting each other. It's a mutualist relationship, right? So this hypothesis, if we dig into it, is that virulence is due to newer interactions between the pathogen and the host. They're not used to each other. The pathogen hasn't adapted to the host. And because it's not quite used to the host environment, and the host isn't used to the pathogen ends up causing disease. And before we even started, Max P asked this question in the chat. Max, great question. I should scroll up and try to find it, but I didn't actually. Let me put this up here. Let me see if I can. Here we go. Here's the question from before we even started. Something that I would like to see is an explanation for why stuff is super virulent. Is it generally just from zoonotic stuff, doing things like it used to before adapting to be less virulent? Great question. So zoonotic here, this is an important word. Zoonotic means jumps from one host to another. And specifically, the word zoonotic means from a different animal into humans. So like SARS coronavirus 2 is a zoonotic virus. It jumped from probably bats into humans, and in humans it causes COVID-19, right? So this is a great question, and this is one of the major hypotheses behind kind of trying to explain virulence, right? It's that you get into a new host, you're not well adapted to that host, that causes problems. That itself causes the problems. This explanation, very attractive, wrong. We like this idea, but it is very wrong. We can't use this as a good general explanation for virulence, and there's two reasons for that. One is you can have very low virulence in emergent pathogens that are new, jumping from one host to another. And there are many examples of this. One of them is pictured right here. This is, again, Ebola virus. Who knew who here knows that there was an Ebola outbreak in the United States in the late 1980s? I think it was 1988, I think it was. It was in Reston, Virginia. There was an Ebola outbreak among workers at a facility that handled monkeys that were being imported for like medical research. And the virus was in the monkeys, and it jumped into humans. Now, Ebola is a new zoonotic infection every time there's an outbreak in humans. It doesn't persistently infect humans. It's not like influenza where it just kind of circulates among humans. So every time it jumps, it's brand new. This strain of Ebola jumped into humans from this research facility I think it was 1988, but I may be wrong about the year, but it was the late 80s, in Reston, Virginia. And fortunately, it was not pathogenic in the humans. There were people who got Ebola virus and did not exhibit symptoms. But as people were like surveying, they were taking blood tests, looking for antibodies and everything. And they found antibodies in these people for Ebola virus that never exhibited any symptoms. They didn't get Ebola hemorrhagic fever. And that's kind of its own strain of Ebola virus. It's Ebola Reston, because all the strains of Ebola are named for where they're found. So there's Ebola Reston is a specific strain of Ebola virus. There was only ever that one outbreak, and it is somewhat unique among strains of Ebola virus, and that it is not pathogenic in humans. Another example of this, of an emergent pathogen with low virulence, is HIV-2. Now, everyone's familiar with HIV-1. That's the pandemic HIV that causes AIDS. And there's actually at least 3, maybe 4 variants. It's HIV-1 group M is the main one. That's what the M stands for, is main. And that's the pandemic HIV from, that spread around the world starting. We realized it in the 1980s. It was spreading before then. But there's also HIV-1 N, O, and P. P is like, but N and O are definitely real. And then there's 2 types of HIV-2. Now, in contrast to HIV-1, HIV-2 has very, very, very low virulence. It's And it's also hard to transmit. It's actually limited mostly to a fairly small area of Western Africa, and it hasn't spread around the world like HIV-1. And that's appeared in humans similar to HIV-1, similar time frame, about the last century or so. So that's a recent acquisition, but it exhibits very low virulence, right? So we have many examples of new pathogens that exhibit low virulence. We also have the opposite, right? We have long-standing virulence in things that have existed in humans for as long as we have historical records going back. So pictured here, this is measles virus right there. We have records of measles going back, thousands of years, right? Another example like this is syphilis, records of syphilis going back basically throughout recorded human history. If this hypothesis was true, that you're going to have this trend towards mutualism, you're going to decrease virulence as the host and parasite adapt to each other, we would have seen that already in these pathogens that have been with humanity for as long as humanity has existed. And we just don't see it. So this hypothesis, really interesting, really good logical hypothesis, we just don't have the support for this. So this cannot answer our question. However, this is biology. So there's always some weird, however, there's always a caveat. We do see for vertically transmitted pathogens, we do see selection for lower virulence. So let's take a minute to answer the question of why that's the case, because that's a really interesting dynamic. First of all, what do we mean by vertical transmission? Vertical transmission is transmission from parent to offspring, in contrast to horizontal transmission, which is I have a cold and I sneeze and you get the cold, right? That's person to person. That's horizontal transmission. Vertical transmission, parent to offspring. Now, in the case of horizontally transmitted things, the host and the parasite are like fighting with each other, right? That is an antagonistic relationship. But in the case of vertical transmission, if you're transmitting from parent to offspring, the fitness of the pathogen is going to equal the fitness of the host. Because if the pathogen gets transmitted from parent to offspring, then every time that infected parent reproduces, that increases the reproductive output of the pathogen itself. And we can illustrate this most simply using bacteriophages, which is what this figure shows. And I'll walk you all through this figure here. So bacteriophages are viruses that infect bacteria. And some types of bacteriophages, not all of them, but some of them, can do this thing called integration. This is where they cut the host DNA, the bacterial DNA, and they stick themselves in there. And they are just part of the host DNA. And this is what's pictured here. So each of these circles, this is a bacterial cell. And this smaller circle within each one, that's the bacterial chromosome. Bacteria, it's not the nucleus, it's just the DNA. They have a circular piece of DNA. And this little red bit right here, that is the bacteriophage DNA that has inserted itself in there. And in that form, it's called a prophage. So now the prophage is integrated as part of the host chromosome. So how does that prophage increase its fitness? How does that prophage increase its own copy number in that particular environment? Well, every time that bacterium replicates, right, it does binary fission. It goes from having one bacteria to two bacteria. Well, now we've also gone from one viral genome to two viral genome. The host doubles, the virus doubles. And then when those daughter cells double, now the virus doubles again. So in this case, instead of the host and the pathogen competing with each other, the host and the pathogen are actually linked with each other. Their fitness is going to be equal. So in this case, the parasite has an incentive not only to not hurt the host, it has an incentive to help the host. Because if that prophage, for example, can make that bacterium, that host cell, replicate more, replicate faster, that also increases the fitness of the parasite. So when you have vertical transmission, that tends to lead to selection for lower virulence. There's some really cool examples of this. So for example, there's bacteriophages of cyanobacteria. These are bacteria that do photosynthesis. They're green. They mostly live in the oceans. And these bacteriophages actually have in their own genome genes that help increase the rate of photosynthesis. So the infected cells actually grow and replicate faster compared to the uninfected cells. Cholera is another example of this, where the cholera toxin that causes the diarrhea that facilitates transmission of the bacteria, that's actually due to cholera toxin phage. It's a bacteriophage that lives inside, it's integrated into the chromosome of the cholera cells. It's not the cholera bacterium that causes the disease, it's the bacteriophage that's integrated into its DNA. Those disease symptoms facilitate transmission, which allows both the phage DNA, the prophage, and the bacterium itself to transmit to hosts more efficiently, right? So we see this dynamic. You even see this dynamic with things like plasmids, where plasmids are basically little bits of parasitic DNA. They're kind of like viruses, but they don't do the transmission in a protein coat to the next cell. So plasmids will often have the genes on board for both antibacterial compounds like antibiotics and for resistance. So if a cell gets infected by a plasmid, it makes a toxin that kills the other competing cells, but it itself gets the resistance gene. So it doesn't get killed by that pathogen. This is a great question from Max P. Any examples of this in eukaryotes? Any examples of vertically transmitted parasites in eukaryotes? So the example that I can think of is viruses, retroviruses, where they integrate into your DNA. Now, oh boy, for retroviruses, let's see. I can't think of an example of an active retrovirus that does this. I can't think of an example off the top of my head. I can think of endogenous retroviruses that are beneficial. So mammals very famously have co-opted an endogenous retrovirus that's beneficial. Somebody earlier here, yeah, Jake, insert clever dapper inside joke. Joke here, Nelson said similar to herbs, endogenous retroviruses, that would be the equivalent for eukaryotes. I can't think of a non-endogenous example of this in eukaryotes. That is not to say that one doesn't exist. I just don't know of any off the top of my head, but that's a really good question. So thank you for that question. Okay, so that's vertical transmission. But horizontally transmitted pathogens don't follow those rules. So great, we could explain the dynamics with virulence if you're being transmitted horizontally, but this rule is not generalizable to things where the host and the parasite are competing with each other. So we have to come up with a better answer for that. Now, one specific kind of dynamic we can talk about is something I mentioned earlier, is the symptoms themselves can promote transmission. And this can lead to selection for higher virulence. Basically, the sicker a virus makes you, or a pathogen makes you, I should say, I shouldn't just viruses, it's anything. The sicker it makes you, the more efficient it transmits to the next host. So that's going to lead to kind of a positive feedback loop, right? The worse symptoms, more transmission, worse symptoms become more common in the population, right? That you can see how that dynamic would work. You get this positive feedback loop of selection for higher virulence. And we do have some data for specific cases that support this dynamic. The example again, I don't know why I keep going back to Ebola, but Ebola is an example of this. So two of the most common strains of Ebola are the Zaire strain and the Sudan strain. And they are a little bit different in terms of their infectivity and their virulence. So the Zaire strain has an R0, and that is a measure of transmissibility, kind of your baseline transmission rate. Way to think of this is just if you have one person infected, on average, how many new infections result from that? So for the Zaire strain, it's about 1.83. Those data come from 1995 in the Democratic Republic of Congo. And the Zaire strain of Ebola has, at least for some of its outbreaks, an 83% mortality rate. Many of them are lower than that, but that's on the high end. Now, the Sudan strain transmits less efficiently. Its R0 is only 1.34. Those data come from 2000 in Uganda. And it has a 54% mortality rate. Again, it's lower, in certain outbreaks. The earlier outbreaks had a higher mortality rate, but I think these are the highest recorded for each of those two strains. Now, why in the world would higher mortality be associated with higher transmission? It turns out that the symptoms of Ebola directly promote the transmission. So what are the symptoms of Ebola hemorrhagic fever? Well, it's hemorrhagic fever, causes bleeding out of every orifice of your body, including your eyes. It's really super gross. And so if somebody has worse symptoms, right, they're more likely to experience more bleeding faster, which means the people around them are more likely to get caught up in it and accidentally receive some of that virus from the fluids that are being lost from the infected person, right? If you want more details in terms of like what the specific symptoms of a hemorrhagic fever look like, one thing I like to do in my classes is book recommendations. Fantastic book, specifically actually on that Reston Ebola outbreak I mentioned earlier, called The Hot Zone. And I actually read this book in college. It was one of the books that got me like into viruses, was The Hot Zone. And it's all about that specific Ebola outbreak, but it's about Ebola and related kind of hemorrhagic diseases and kind of the dynamics and the countermeasures and all that stuff. So highly recommend that book. And it explains kind of the symptoms of a severe Ebola infection and illustrates very vividly how, yeah, as Little Pink Bowser says here, more blood equals more people touch the blood equals more people infected. Yeah. That's exactly the dynamic, right? The worse symptoms lead to more transmission. Okay, so that's another thing that can happen. That's another dynamic that could be at play here. There's a really interesting specific case of this. This is specific to diseases that are vectored, meaning they're transmitted from one person to another with some kind of intermediate host, like a mosquito is the most common way of thinking about this. So like malaria is an example of something like this. And these dynamics are called too sick to swat, where higher virulence among a vectored disease leads to a decreased ability to fight off the insect vectors, which leads to higher levels of transmission. So this graph, there's a lot going on here. Across the x-axis, we have virulence, so low on the left, high virulence on the right. And then the blue y-axis here is transmission. So low virulence starts off with very low transmission, because if you're not sick and like they're mosquitoes, you're going to swat at the mosquitoes. You're going to keep them away. As you get sicker, right, what's going to happen to this other y-axis over here, swatting in red? If you're not experiencing symptoms, you're going to swat a lot. As you get sicker, that's going to decrease your ability to fight off the mosquitoes until you basically have no ability to fight off the mosquitoes. And that maximizes the transmission until, of course, an infected individual dies, and then mosquitoes don't bite dead things, right? So then the transmission falls off if the patient dies. But as long as you stay alive, but unable to swat away the disease vectors, that's what maximizes transmission for vector diseases. And this is called too sick to swat. That's what this dynamic is called. So this one, I'm actually going to show you a bit of data for this one, because we do have, I think, reasonable support for this. So this figure here shows the mortality rate in different bins. So you've got less than 0.1%, 0.1 to 1%, and then 1 to 10, and greater than 10%. And frequency across up and down the y-axis here for two different types of diseases, vector-borne in red and direct transmission in blue. And what we see for directly transmitted diseases, so just I sneeze, you get the cold, that's direct transmission, right? Most of those have very, very, very low virulence. And 0.1% is even higher than most diseases. You're going to have a few more places after the decimal there in most cases. 0.1 to 1, even at that point, that's once you start getting near 1%, that's like a pretty high mortality rate. And directly transmitted diseases, quite low. Very few of them are above that 1, and certainly very low below above the 10%. But then if you look at the vectored diseases here, you see that it's only a plurality that are in that least virulent category. And it's a pretty flat distribution from 0.1% to more than 10%, markedly more virulent on average compared to the directly transmitted diseases. So given these data, it seems like that too sick to swat hypothesis does a really good job explaining the virulence dynamics around vectored diseases specifically, which, hey, great. We have another specific, very limited case, but we have what seems to be a good explanation for that limited case. Okay. So I like that one. That seems like a reasonable answer for those limited cases. So generally, here's what we've arrived at so far. Here's what I want you to be taken away at this point, right? Virulence will be adaptive to the extent that it facilitates rather than inhibits transmission. If virulence is helping you, spread through the population, get to new hosts, then great. Virulence is going to be adaptive. It'll be selected for. And more broadly speaking, we can be more general than that, right? Take it out of the realm of transmission. We could say virulence will be adaptive up to the point where it becomes a net drag on pathogen propagation or pathogen fitness, right? So virulence is good unless it makes your host too sick, and then it becomes a problem, is kind of a general way to think about this. But here's the thing. This sounds fine, but this is a bit tautological, isn't it? It'll be adaptive until it's no longer adaptive. Duh. Yeah, it'll be adaptive until it's not. Sure. Why? We still haven't answered the question, why is that the case? How does that actually work? So now, in our last section, we're going to actually answer that question. And this, everybody, this is where we get into the really cool stuff. This is the fun part. I've been looking forward to this since we started. So in this last section, we're going to talk about intra and inter-host competition. And that or should not be there. That should pop up later. This is what happens when you work on your slides like right before you start, which I always do. In my real classes, I'll be up there in the front of the room on my laptop, like tweaking my slides right before class starts. That's what I do. So in most cases, what we can look at in a disease as it works its way through a host population is that the rate limiting step in the pathogen's life cycle imposes selection either for or against virulence, depending on what that rate limiting step is in the life cycle. So it could be that it's relatively easy in the context in which a particular disease exists. It's relatively easy to spread from host to host. But within host competition is really hard compared to spreading. So you have to fight for kind of winning the competition within a specific infected individual. Or the challenging step, the thing that limits your fitness, is spreading to a new host rather than that within host competition, right? So it's the transmission step that's the bottleneck in your life cycle, and that's going to be a different set of selective pressures. Are there any instances, let me see this question here. Are there any instances where low virulence and high virulence are adaptive, but intermediate virulence is actually maladaptive? That is a fantastic question. Wow, that's a really good question. Yeah, I think so. I think we could probably think of examples of that. If, by the way, this is what happens in class all the time, is somebody will ask a question, I'll be like, I never thought of that before, but let's think through it. That's a really interesting question, right? So low vir, and this is like classic disruptive selection, right? Where one extreme of the phenotype is good, the opposite extreme of the phenotype is good, but the intermediate phenotype, no good, right? This is classic disruptive selection is what that's called. I'm sure there are, but more generally, we can often kind of think about pathogens as pursuing one of two strategies. But I can't think of any cases off the top of my head where either strategy works well and an intermediate strategy is not good. But man, that's a really good question. I'm going to be thinking about that one for a while. If anybody else in the chat has an example of this, I'd love to hear it. I can't think of one off the top of my head. I'm trying to think how that would work. Man, that's a really good question. Thank you. Good question. This is why when I do my classes for real, sometimes like I just don't finish the class. Like we get to the end and I still have 10 minutes of stuff to do because like That happens, and then we go down rabbit holes. But we're not on the clock tonight. We're just chatting, so it's fine. So let's talk about these dynamics here, okay? So in order to make sense of this, we have to define the two kind of realms of competition we're talking about. So first, we'll start with intra-host competition. Within the context of intra-host competition, the pathogens are competing with other pathogens within their current host. And they're also competing with the host itself, right? You have to fight back against the host immune system here. Okay, so the question that's relevant to intra-host competition is who dominates the population in the current host. So you have a host that has a lot of different genotypes, right? Each of these dots represents a genotype of a specific pathogen. And over time, they're going to compete with each other. And one particular variant might come to dominate that population. This illustration here, this is intra-host competition. All right, that's intra-host competition, competition within a single host. Now, the other level of competition is inter-host competition. This is where pathogens in one host are competing with the pathogens in other hosts for access to potential future hosts, people who haven't yet been infected by this particular pathogen, right? So the question here is, in this competition, who wins the fight over those future hosts, right? So inter-host competition is all about transmissibility. Who transmits from one host to another most efficiently? Okay, so we've got inter-host competition, we have intra-host competition, and when those two different levels of competition are the rate-limiting steps, we see different selection dynamics related to virulence. Is everybody with me with inter versus intra-host competition? So we're just about at the end here. We're gonna do it. But I just want to make sure if anybody has any questions about inter versus intra-host competition, ask now so we can clarify before we see how these dynamics lead to different types of selection for virulence. I think I've given everybody enough time here in the chat. I don't see any questions, so I'm going to keep going. But if you have any questions, feel free to ask. We'll jump right in. So, scenario number one, intra-host competition dominates. In this situation, spreading to a new host is really easy. So this part of the viral or pathogen life cycle, I was thinking viruses, but it could be anything. This part of the pathogen life cycle is easy, right? There's lots of hosts that are available that are susceptible, they've never been exposed to this pathogen before. So transmission is really easy, right? That means that this step is going to be where you really make your money, right? If you can dominate that population, you're going to win. You're going to transmit to lots of other hosts. So the winning strategy here, if intra-host competition dominates, if it's easy to get to your next host, the winning strategy is to just dominate the population in your current host. Now, this leads to very specific traits in terms of selection, right? You're going to select for what we think of as better infectivity in that host. You're going to do a better job fighting against the other pathogens. You're going to infect the host cells faster. You're going to replicate faster. You're either going to effectively evade the immune system or damage the immune system. These types of traits that are now experiencing selection, right? You're selecting for those traits, that's going to lead to more damage to your host and therefore higher virulence, right? You're going to make your host sicker. That may, in some absolute sense, reduce your opportunities for transmission, but it doesn't matter because new hosts are really easy to find. That's not the rate limiting step. If you don't win this competition under these ecological conditions, you're not getting to the next host. So you better win this competition, even if it causes more harm to your host. Now, the flip side of those dynamics is we have a situation where it's really hard to find a new host. Inter-host competition is going to dominate. It's going to be the rate limiting step. Okay, so in this scenario, finding a new host is really hard to do. There just aren't that many susceptible hosts out there. Maybe the population of potential hosts is really low density. Or maybe everyone's already had the disease, right? Maybe you're in, I don't know, hypothetically year 5 of a global pandemic, and everyone's been infected with the pandemic virus at least twice at this point, right? Whatever, or everyone's been vaccinated, right? Whatever the case is, in this situation, it's really hard to find a new host and transmit to that new host. So the within host competition, the intra-host dynamics are going to be secondary to just being able to get out there in the world and find a new host. In this situation, the winning strategy is to maximize your chance of transmission, because it doesn't matter if you win this race, if you dominate your intra-host competition, it doesn't matter if you never encounter another host to transmit to, right? So this leads to selection for a longer infective period and slower replication, which leads to less damage to the host and lower virulence. So when inter-host competition dominates, that's where we see selection pushing back on virulence, and you lead to less virulence to maximize the likelihood of transmission. And as Little Pink Bowser put it right here, so you min-max your bottleneck. Exactly. That's basically exactly what you're doing, right? Is the bottleneck within the host, then you go all out, win that competition. Doesn't matter if you kill your host fast, because you're going to spread. And if the bottleneck is getting to the next host, you really slow things down within that original host to make sure that you don't hurt them too much or kill them before you have a chance to spread. Exactly. You min-max your bottleneck. Great way to think about it. I love it. How's everyone feel? Is everyone okay with these dynamics? Is this kind of making sense to everybody? Are we doing okay? So I'm going to show you some data that actually support this. And I really love this experiment. This is an experiment, again, on bacteriophages that illustrates this exact dynamic. So what we found in this experiment, and I'll go through the graph in just a second. What we found in this experiment is if you take bacteriophages and you give them lots of hosts, you have high density of their bacterial hosts, they replicate and burst those host cells really fast. Because how do you win? You just take over as many hosts as you can as fast as you can, right? That's how your genotype becomes the most common genotype. Now, if you have bacteriophages with a few hosts, just low density hosts, you're going to replicate and burst more slowly. You want to slow it down. Make sure you make a lot of viruses in the host you're currently at before you burst it and kill it. And you don't want to leave too soon. You want to make sure you're maximizing your chance of finding another host in that low density host population. Okay, so here's data on this, looking at viruses that are adapted for high and low density host populations. So across the x-axis here, we have post-eclipse time. And this goes back to that graph I showed you way back at the very beginning, showing how when a virus gets in, right, it goes from one virus to no viruses before it starts making new viruses. The question is, how long is that time period, right? And on the y-axis here, we just have fitness for those viruses as measured in doublings per hour. So how many times per hour does that virus population double? Okay, that's just kind of the traditional way of measuring viruses. You measure the doubling time or the doubling rate. So let's look at these two curves, the data from our two host populations. So right here, we have our high density hosts. And what you can see is they have very high fitness in terms of doublings per hour, right? On high density hosts, it's really easy to find a new host. So what you need to do is get into your current host, make a bunch of viruses, and get out as fast as you can. That means you're replicating fast and you're killing your host really fast because it's easy to find the next host in line. So we're having higher infectivity. You're selecting for being really good at competing in your current host. As a result, you have very high virulence. Now, in our low density host population, things are different. Because if you get into your host, you make a couple of viruses and you kill it right away, if the hosts are low density, you might not find a new host. And then it doesn't matter if your genotype won the competition within that previous host, because that host is dead and you haven't found a new one. So your lineage is now extinct. Your fitness is now 0, right? It doesn't matter. So what we see in the low density host population is we see slower replication, right? The doublings per hour, instead of being, 40 doublings per hour, it's, 10 to 12 doublings per hour. But look at the amount of time those viruses will spend in their post-eclipse time period in their host, right? It's a much longer period of viral production, and that's going to facilitate making more viruses before you burst. Basically, I got a good thing going here. I don't know if I'm going to find a new host, so I better stay in this host and maximize my replication before I go out into the world to try to find another one, right? That's the dynamic that's at play here. Okay, so we have from the vibratory encapsulation of Puget Sound, we have, are they set to either rapid expansion or slow, but whichever mode is better is the one that wins out. Yeah, the basically replication rate, infectivity, burst time, these are all phenotypes for viruses that are under selection. So somebody asked, it was same person said, what triggers that? What regulates their rate? Basically, they're not like consciously perceiving their host density. This is the beauty of natural selection. It's not an intentional process, right? So if you have low density hosts, right, and you have one strain of bacteriophage that gets in, makes a few and bursts, and another strain gets in, takes its time, makes a lot and bursts later, which of those two genotypes is going to have better success finding hosts? It's going to be the slower replicating one. If you have a population where the host density is very high, right, a slow replicating kind of, we'll call them like a careful virus, gets into that high density host population, while it's sitting in its host, replicating and making lots of viruses and not killing its host, the ones that get in, make a couple and burst out, have already infected a dozen subsequent hosts at that point, right? So it's the fast replicating one in that high density population that takes over. Right. So there's no, the trigger is there's going to be different alleles that lead to different rates of replication, and selection dictates which one is going to be optimal given the ecological conditions. Right. Do we have cases where host density has changed for a virus? Absolutely. This is how pandemics work. There's a reason that viruses are most virulent early in a pandemic, and then the virulence tends to taper off. And we saw this, the quintessential example of this is the 1918 influenza pandemic that killed in its first year and a half, probably 100 million people. But that virus kept circulating through the 20th century. It's still out there, the descendants of the 1918 flu pandemic. But viral mortality rates were only elevated throughout the 1920s, and it was only catastrophic in that first year and a half or so. And the reason for that was in that first year, everybody was susceptible to it. That was a zoonotic transmission from, I think it was bird flu. Everybody was susceptible to it. So it illustrates the inter-host competition dynamics being the rate limiting step, where the challenge was winning within the host, but literally everybody in the world was susceptible to that virus. So there was no challenge in getting from host to host. Now you fast forward 3, 4, 5 years, most people have been infected with that virus around the world, and a lot of people died. And then once you're infected, you have antibodies and you're less susceptible going forward. So now that flips the dynamics. So now you're in a situation where inter-host competition is dominating the selective pressures, and that flips the selective dynamic with regard to virulence. So yeah, this is a thing that we can directly see. We've documented this. And piggybacking on this from Robert Adsett, great connection, vaccinations change the pressure to favor low virulence. Potentially, yes, by switching the selection dynamics to basically imposing more stringent inter-host competition that could potentially be a thing that happens. Yes, absolutely. You're making it harder to transmit. You're going to lead to selective pressures that may, I'm not going to say it as an absolute, but it may reduce virulence. Yes, absolutely. I love it, everybody. You're seeing how this works. You're making the connections. It's what I love to see. So let's continue here. We're just about done here. We're doing great, everybody. So here's the big picture. If it's easy to spread from individual to individual, then you want to take over your current host as fast as possible. And it doesn't matter if you hurt them or kill them, it's really easy to find a new host. But if it's hard to spread, it doesn't matter if you take over your host, because if your host dies, let me say that clearly in English this time, it doesn't matter if you win the fight and take over your host if your host dies before you find a new one. So it's a better strategy to slow down and make sure you find that next host before you do too much damage to your current host. Okay, so we have kind of an opposite dynamic here, depending on, again, whether that bottleneck is the inter-host competition or the intra-host competition. That's the big takeaway here. So to summarize what we talked about tonight here in the last hour and change, I'm surprised this took so long, but this was good. Virulence is a trait that can evolve in pathogens, but it's not just a specific trait of the pathogens. It has to do with all sorts of complicated evolutionary dynamics, right? You can select for or against virulence, and that's going to be due to the transmission method of the virus, competition between pathogens that could be within the host or between different hosts, competition between the hosts and the pathogens, and the ecological conditions in which all of these interactions are taking place. Is there a high density of potential hosts available, or is there a low density? Is there strong competition within an individual, or is there weak competition within an individual? These are all different kind of factors that go into the stew that leads to the selective pressures that are going to contribute to the evolution of virulence in, whatever different pathogens we are going to see. So that is where we are going to leave this one. What I always do in my real classes, and I'm going to do it here, is tell you what we're going to do next time. So next week, we're going to come back, we're going to do something just like this. But instead of talking about virulence, we're going to talk about altruism, because altruistic behavior seems like something that's really hard to explain via natural selection. How can you select for something that when you exhibit that trait, when you do the altruistic behavior, it actually hurts your own fitness? How does that work? Well, it turns out we have a really good answer for that. So we're going to explain exactly how evolution explains altruism. That's going to be next week, same time. So that's going to be Wednesday, the 17th of July at 9 p.m. Eastern Daylight Time, right back here. So thank you all for being here, everybody. I hope you really enjoyed that. I do need to, just before we go, point out a super chat from Barnaby Wild for $2. It says, I never know what you're speaking about, but I try. That was in response to my question of how's everybody doing? Are we following along? So Barnaby, I hope you felt like that was you could follow that. But next week, we're going to come back and do a similar thing. It's going to be super fun. And then the week after that, we're going to do it again. We're going to talk about cancer evolution. Those three things may seem unrelated. They're actually, as we're going to see, they're all connected. They're all going to, build on each other, and it's going to be the same dynamics at play. So I'm really excited. Before you all go, please hit like down below and share this video. This is really different from what I normally do. So I don't know how this is going to fly and what people are going to think. But yeah, that's it. Oh, wait, don't leave. We have questions. You know what? Hit me. What are your questions? Sorry if I missed questions in here. What are the questions? Because can this framework explain why diseases like Ebola? Yes. We talked about that. It was that the symptoms of the disease facilitate transmission. So higher virulence, specifically in Ebola, actually is correlated with greater transmissibility. So that actually, it does a really good job explaining that. Yeah. Let's see. That was an thank you. Oh, Vibratory has one. Hang on. I'm looking for the questions, everybody. Oh, here we go. How does this intersect with STIs, sexually transmitted infections, especially the ones that have immediate painful symptoms like a burning sensation? That is probably like an incidental symptom. It's not something that's being selected for, right? Because you could imagine that would reduce opportunities for transmission. Yeah. And then endogenous retroviruses, vertical transmission. And endogenous retroviruses are no longer harmful, right? The non-endogenized versions, the active retroviruses, right? Those cause disease. The endogenized ones are they don't hurt us, right? And that tracks for vertical transmission. We see evolution away from pathogenicity in vertically transmitted I'll say organisms. Yeah. Good. Okay. Oh, where does this leave us with viruses that have been around forever that are still virulent? Polio, smallpox. Yeah. There's just, some things, there's just no equilibrium point, right? You're not necessarily going to evolve away from virulence. And you just gotta, vaccines are the only way out of that one, I guess, right? Okay. I think that's it, everybody. I think we can call it a night. Oh, one more question here. That's something we didn't talk about was asymptomatic but still transmissible infections and kind of incubation periods. And that's what's going on with a lot of STIs where, yeah, you have terrible symptoms, but that are not all the time, right? So it can be transmitted in other times. The disease is still present, but the symptoms are absent, right? So that's what's going on there. Alrighty, thank you all again, everybody. I appreciate you all being here and hanging out with me, letting me just talk about this stuff because I think it's interesting. So I hope everybody has a great night. You found that enjoyable and informative. I hope you feel like you learned something, and I will see you back here next week for a similar thing. Good night, everybody.